Hi, this is a video on factorial notation, what it is, what it's used for, and how you can simplify expressions using factorial notation. Factorial notation, first off, is just a means of expressing repeated multiplication of descending numbers. Therefore, it would be something like 3 factorial, that's the symbol for factorial, is equal to 3 times the number below it, which is 2, times the number below it, which is 1. If you multiply those together, you'd actually get equal to 6. And that's an easy one, but it's an illustration of what you do with factorial notation. It is programmed into your graphing calculator. Really, any scientific calculator will have it, although the questions we're going to do now will not require a calculator. And that's really all it is. For something like 3 factorial, it doesn't require much of anything. It's a simple enough one. But when you start seeing bigger numbers or algebraic expressions with it, it comes in handy. So just for the actual definition of it, n factorial would be equal to n times n minus 1 times n minus 2 times n minus 3 all the way down to 1. And this is important. This can actually throw people off until they get comfortable with it. When you write n like that, in that form, and then n minus 1, that just means you're going down by 1. And then n minus 2 means you're going down by another 1, and then by another 1. So that's how we express descending order of numbers. N minus 1, n minus 2, n minus 3, all the way down. Something else we should be aware of is that n has to be an element of the set of whole numbers. We're always dealing with whole numbers, no fractions, no decimals, anything like that. No negative numbers. And what you're probably thinking right now is this stops at the number 1. What about 0? 0 factorial is equal to 1. So we'll accept that for now. There's a illustration, a proof of that, which I won't bother doing. The rare times you see 0 factorial, you just need to replace it with a 1. Will show up once in a while. So let's take a look at a few questions and then work through them, gradually making them a little more difficult. To begin with, we will expand some of these. Expanding means we don't need to come up with an answer or anything, we just need to write it out. So 6 factorial, well, what this really means is 6 times 5 times 4 times 3 times 2 times 1. If you work this one out, it would be equal to 720. But you don't need to do that. And that's it. Just going down by 1. Nothing to it. Now 11 factorial, same idea. 11 times 10 times 9 times 8. And I'm going to cheat. I'm just going to go all the way down to 1. We know what's coming next. Just going down by that. And that's a bigger number. So I'll save that for a calculator to evaluate, should you want to do that. The next one is 120 factorial. Now this is getting completely out of control. So let's just take it down for a few of them. So 120 times 119 times 118 all the way down times 117, 116, etc. till you got to 1. So that's a very, very large number. So you'll be glad that you have a factorial key on your calculator to work these ones out, because it can be a bit of a pain. Now, in actual fact, when we start seeing numbers like that in a question, we will simplify them and work them, simplify them first before we do anything. So it's not as big a deal as you might think. Now, n factorial, we saw this one earlier in the actual definition of it, but let's go through it again. This would mean n is unknown. We don't know what number we're talking about, but we do know the number following n is n minus 1. Just subtract 1, that's all we're doing. And then the number after that is going to be n minus 2, whatever n was. And then n minus 3, then n minus 4, and eventually we have to stop this all the way down to 1. As I said earlier, that is an important feature of the simplification of these, and we'll see that with this next question, because we're not starting at n anymore. We're starting at n, whatever n is, plus 2. We do the same thing, though. We start with n plus 2, the very first number, and then we recognize the number. If we subtracted 1 from that, it's just going to be n plus 1, just going down by 1. And then the one below n plus 1 is just plain n. That one is gone. And then we get n minus 1 for the next one. Now we're on more familiar ground, all the way down to 1. Nothing to it. Let's try another one. 3n minus 1 factorial. Can be a little confusing because there's a more complex expression within the bracket, but don't overthink it. We start off with the first one, which is 3n minus 1. Well, 1 down from that is just going to be 3n minus 2. Sorry about that. 3n minus 2. Because we're subtracting 1. So we just subtract 1 off the 1. And then the next one is going to be 3n minus 3. And then 3n minus 4. Now you can go on as far as you want, but I'm going to stop right there and then just go all the way to 1. So once you get used to this, it's not very difficult. You just have to remember you're subtracting 1 off the number and going down and down and down and down until you basically decide to stop and then just dot, dot, dot to 1. We will see simplification questions shortly where we can do a little more though. In fact, it's coming right up. So this you will do a lot. So you get questions like this, 17 factorial over 13 factorial. Now some of you may just key that into your calculator and work it out, and that's fine, but you'll see there's a real fast and easy way to do this. And really the key for this is you take a look at the two numbers, and they're usually written, in fact, I'd say always written in a fraction form. So 1 factorial over another factorial. The trick is to break or expand's a better word, the big term until it equals the small one. I'll show you what I mean by that. It's fairly easy to see with numbers as opposed to the variables which are coming up. But 17 factorial is larger than 13 factorial. So what I'm going to do is I'm going to expand that 17 factorial until it's equal to 13 factorial. So what that would mean, or what look like, is 17 factorial is going to be 17 times 16, right? As always, just down by 1, times 15, times 14. And I keep my eye on the denominator, because when I get to 13 and it keeps on going, I see, hey, 13 factorial is on the bottom. And I recognize if I just keep that factorial on top, that just means onward down to 1. So I can stop there with that 13 factorial. And this can now be canceled out. So this really is the only way to cancel out factorials, because we don't really, when we get into variables at least, we don't really know what the end variable means. So this would turn into 17 times 16 times 15 times 14. And we used to do this a lot before we had good calculators. Now, you know, it's a less common procedure. But that's the idea. You break the big one down until it's equal to the small one, and then once it is, you can cancel out the factorial symbol. 13 factorial divided by 13 factorial. The second one is kind of the same idea, except with this, we've got the bigger number on the denominator, which is fine. So that's 5 factorial. Excuse all the writing we've got in this one. But I'll take that 8 on the bottom, and I'll do the same thing. 8 times 7 times 6. And then once I get to 5 factorial, or 5, I can just express that as factorial, because that factorial just means and so on and so on. And then I know that they're equal, so they cancel right out. And then this becomes, well, there's still a 1 on top, and that's 1 over 8 times 7 times 6, which I'll leave like that. The big one until it's equal to the small one. So then we get something like this. And if we do get something like this, we then have to recognize, even though there's no numbers exactly for this one, there are numbers, but there is also an n. We got to recognize that the n plus 3 is bigger than the n. Whatever that n number is, n plus 3 is larger than n. So this becomes, I'm going to take it over to the side here. Sorry, everybody. Just follow along with that if you can. N plus 3 is going to break down into n plus 3 factorial, sorry, will be n plus 3 times n plus 2 times n plus 1. And then I go one more, and look what happens, n. And that's the same as the number on the bottom, n factorial. So I just keep that n factorial going on top, or I express it with that. And guess what? Cancel these guys out. So we end up with just that. N plus 3, and I'm going to leave it like that just because I'm lazy. N plus 3 times n plus 2, sorry, n plus 3 times n plus 2 times n plus 1. And you may think, well, what's the big deal? How much better off are we with that than we were before? Well, the key is that we got rid of the factorial symbol. Getting rid of that factorial symbol allows us then to simplify these expressions, like and to actually solve for something. Shortly, we'll get to that. But let's do a few more of these. So number 4 is n minus 1 factorial over n plus 2 factorial. Once again, we need to recognize which is bigger. Now, n plus 2 is bigger than n minus 1. Whatever that n number was, 5, 6, 7, could be anything, you add 2 to it, it will be larger than that number, subtract 1. So I'm going to break the denominator down. I'm going to keep that n minus 1 as is. So n minus 1 factorial. Not make any changes, but that n plus 2, well, the number below n plus 2 is n plus 1. And then the number below n plus 1 is just n. Keep in mind, we're just subtracting 1 from that. And then we're going to get to n minus 1, and here we are. Because now we're equal to that numerator, it's gone. And now we can express this one very cleanly as 1 on top all over n plus 2 times n plus 1 multiplied by n. Nothing to it. Let's do one more that's a little bit different and less useful, actually. You'll see that there is no factorial symbol on the bottom. Now, normally this would be a problem. In fact, for practical, I mean, if you could call any of these practical, the factorial sign we'd want to cancel. In this case, we can't really do that because there's no denominator. But I was going to still break that numerator down, because the numerator would be n times n minus 1 times n minus 2. So I hope that makes sense, just going down by 1. And then I see there is an n minus 2 down below. But I'm going to go one more in this case, and then I'm going to go factorial like this. And then the denominator has got a 3, and it's got an n minus 2 on the bottom. And really all that's happening here is that we're canceling out those n minus 2s. And we don't get much for it. We just get n times n minus 1 times, sorry about that. This would be n minus 3. Can I not? There we go. You guys, everybody's wondering what's going on with that. It's the problem with these videos. Nobody, if this was a class, somebody would tell me right away that there's a big mistake there. All over 3. Now, this question does not really do much for us, but it is practice in breaking down factorials. Where this is leading is equations to solve. So let's try a couple of those and then call it a wrap. So now we're looking for that mysterious value of n. Now, a lot of you will just plug in numbers in your calculator and see what works. And can't say it's the wrong thing to do, but there is a good algebraic method for this one. So let's take a look at this. As always, we take a look at the two factorials and we identify which one is larger. I hope everybody agrees that n plus 2 factorial, or just plain n plus 2, is larger than n plus 1. I will break that n plus 2 down. So we get n plus 2. And we're in luck with this one because we just go down to the next one, subtract 1, it's n plus 1 factorial. And we see, aha, that's going to cancel on the denominator. We can't forget, however, that there is a 9 on the other side. But first, let's clean this one up. The n plus 1 factorials go away. And all we're left with then, if we move to the right, which is what I'm going to do, we're left with n plus 2 is equal to 9. And then we subtract 2 from both sides to solve this equation, nice simple one, and we get n is equal to 7. Now the second one, and the last one I'm going to do, is a little more complicated. We don't know that at the start, but once we start simplifying this, we're going to see, yeah, there's some things going on here. Now, not a super complicated one, but the algebra is a little bit more complex. So n plus 2 over n, and the n plus 2 is larger than n. It has to be. We're adding 2 to it. But we don't think too far ahead. We just take that n plus 2, and then we break it down to n plus 1. You may peek at the denominator, but it's not good enough yet. It's not going to cancel. However, the next term is n, and that's the one that's where we can stop, because the n factorial on the bottom now is going to cancel. So things are looking good. We got rid of the factorial, and we got n plus 2 times n plus 1 is equal to 6. However, we have a more difficult equation to solve. This is going to turn into a quadratic equation to the exponent of 2. And if you haven't factored or worked with those for a while, you may need a bit of review. You're not going to get super complicated ones, but they do show up in this section. But what I'm going to do first is to expand these two binomials on the left, I'm going to use the old FOIL method, which is first, outer, inner, last. So I multiply the two first terms together, which is n squared. N times n is n squared. I do the two outer terms together, so that's n times 1, so that's plus 1, n. I do the inner terms, so 2 times 1, 2 times n is 2n, and then I do the two last terms. So that's what FOIL is. First, outer, inner, last, plus 2, all equal to 6. And then, as typically happens with these, the OI part of FOIL, the outer and the inner, can be combined because they're like terms. So we get n squared plus 3n, 1n plus 2n is 3n, plus 2 is equal to 6. Now the way we solve these quadratic equations is we bring all the terms over to one side. So I'm going to bring them all to the left, and that means I'm going to subtract this 6 away from both sides. And we get n squared plus 3n minus 4 is equal to 0. Just going to take this guy up here to get a little more space to work this one out. And then we're going to do the reverse of FOIL. That is, we're going to break this down into two binomials. So what we're going to be doing is we're going to be looking for, I'm just going to write it up here again, n squared plus 3n minus 4 is equal to 0. We're going to be looking for two numbers that multiply to that minus 4. And have a sum of the middle number, which is plus 3. So just take a look at the coefficients. I will say at this point, if you're not familiar with this method and you're taking my course, I put some extra information, some review material on factoring, and that will help with this step. But if it's making sense to you, you would have done these before at some point, then follow with and then do some of the practice in the exercises, and then you'll be fine. Because what we're going to do is, when we find these two numbers, if they have a product of minus 4, they could be 1 and 4, they could be 2 and 2. But I'm going to pick these two numbers 1 and 4, and if I make this 1 negative, which is what we want to have a product of negative 4, negative 1 times 4 is negative 4, but negative 1 plus 4 is equal to 3, which is what we want. So this breaks down into n minus 1 multiplied by n plus 4. And if we were to do FOIL on this one, it would take us right back to n squared plus 3n minus 4. You could check it out. First times first, outer times outer, Inner times inner, last times last. And what we do to solve this one, because we're looking for an answer, perhaps 2, is we take each of those factors and go n minus 1 is equal to 0, and n, or I should say, n plus 4 is equal to 0, and we solve away. So we add 1 on to both sides to solve for that equation, so we get n is equal to 1 here. And then on this one would be subtract 4 from both sides, so we get n is equal to negative 4. You cannot have a negative number when you solve this one, because then you can't take the factorial of a negative, and when we do take a look, a quick check will show you that that's not possible. Negative 4 factorial is inadmissible, so we reject this one. And our only answer is n equal 1. So that's a quick introductory lesson on factorials and some of the questions you're going to get. You do want to do enough of these so you're comfortable with it. They're really not that hard. Never mind this last bit of factoring that we did to solve this. The basics aren't that bad. They look worse than they are. And so a little bit of practice, you can get around that. Thank you.